In this video, we are going to look at the Euler equations used to solve second-order differential equations that has non-constant coefficients. To motivate the discussion, I will ask you to consider solving the problem t squared y double prime of t plus 4ty prime of t plus 2yt equals 0. Take like 10 seconds. Think about how you would start approaching this problem. If I were not aware that there was some danger ahead, I probably would have tried to come up with a characteristic equation. But the thing is, the characteristic equation is good when the coefficients are constant. So maybe this heading gave it away. Whereas here, this coefficient, this t squared is not a constant. T squared is the variable that y depends on. So you can't rush ahead and figure out the characteristic equation and go from there. What you need are the Euler equations. So they apply to differential equations of this form, which this is one of. Here we have the t squared, our second derivative with respect to y. Here a is equal to 4, and then we have t, our first derivative with respect to y. Here beta is equal to 2, and then we have our y. And what we do in this Euler's equation is we use this substitution, x equals natural log of t, so that we can transform this equation here to our normal second order differential equation that we can solve. With this x equals natural log of t, now we're going to make y a function of x, which is a function of t, so a composite function. But with this function composition, we need to consider what this does to y double prime and y prime of t. In other words, we need to figure out dy dt. In order to see how this is going to work, the first thing we need to do is look at this first term here, the d2y dx squared. So the first thing to note is dy dt. So we're going towards d2y dx squared, but we're going to take the first derivative first. So dy dt, so if y is a function of x, that is then a function of t, we would have to do, to get dy dt, we would have to do dy dx and then dx dt. This is simply the chain rule. So for example, if we had x is equal to natural log of t and y is equal to x squared, in other words, y is equal to natural log of t squared, we could take this derivative, and you know this from your first year calculus, you would do the 2 and the natural log of t, but then you need to take the derivative of what's inside, which would be 1 over t. And another way to express this using this chain rule here is that if I take dy dx, the derivative of y with respect to x is just equal to 2x. And then plugging in x equals natural log of t, I get natural log of t. And now if I take dx dt, well, the derivative of x with respect to t is 1 over t. So then dy dt, according to this formula here, would be equal to my 2 natural log of t times 1 over t, which is essentially the same thing. Well, actually, it's exactly the same thing that I got over here. Would be my dy dx times my dx dt. So looking at this again, dy dt is equal to dy dx, dx dt, and in this case, since x is equal to natural log of t, that's the substitution we use in this transformation. So dy dx dt is equal to 1 over t. So this is our first equation. Now let's look at d2y dt squared, which is our first term here. So this is the second derivative of y with respect to t is equal to the derivative of dy dt, the first derivative. So you basically take the first derivative and then you take another derivative. Well, we already said that dy dt is equal to dy dx 1 over t. So that's this here, which is why they're both underlined in green. So I have d dt of dy dx 1 over t. By the product rule, if I take the derivative of a product, so this is our first factor, this is our second factor, d dt of this product is going to be d dt dy dx times this factor here, 1 over t, plus Now we're going to have our dy dx times the derivative of our second factor, which is minus 1 over t squared. Again, from here to here is the product rule. We're taking the derivative of two factors, right? The product of these two numbers. The first one is dy dx. The next number is 1 over t. So we have the derivative of our first factor times our second factor plus the derivative of our second factor times our first factor, product rule. This here is just the second derivative of y with respect to x. This here is dy dx. What did I do here? Oh, I just pulled out the negative sign here. This here is a second derivative where we take the derivative first with respect to x and then with respect to t. So that's the same thing as doing the derivative here with respect to t and then with respect to x. So you can change the order of derivative. That's all I have done from this step to this step. And again, to kind of give you an example of exactly what I'm saying, this is not quite the same form, but it's a better way of illustrating this. If I have a function y that's dependent on t and x, I can take the second derivative of y, first with respect to x and then with respect to t. So in other words, first I'm going to take dy dx, and then I'm going to take the derivative of dy dx with respect to t. So what I'm going to say, what I claim is that's the same thing as taking dy dt and then taking the derivative with respect to x of dy dt. So I can actually do d2y dt first and then dx. So these two, it doesn't matter if I take the derivative with respect to x first or with respect to t first. And an example here for y equals t squared y to the third. So d dt, if I take the derivative with respect to x first, I'm going to get 3t squared x squared. And then if I take with respect to t now, I'm going to get 6tx squared. So again, this is the derivative taken with respect to x first and then t. If I did the opposite direction, I take the derivative with respect to t first and then x, I would get d dx, and then with respect to t, I'd get 2tx to the third, and then with respect to x, I get 6tx squared. So it's the same thing. That's essentially what this is saying here. If I have a second derivative of y, first taken with respect to x and then with t, I can actually take the derivative with respect to t first and then x second. That's what this line is about here. And I know dy dt, I keep using this over and over, is dy dx times dx dt. dx dt is equal to 1 over t. So I have 1 over t squared. That's this line. And then finally, here, this is just derivative of y, second derivative of y, taken with respect to x twice. And why did I do all of this? I went through a lot of trouble. It's because I wanted to get this here, d2y dx squared. And I'm going to move this equality, this equation, the d2y dt squared is equal to d2y dx squared times 1 over t squared minus dy dx 1 over t squared. So it's here underlined in green. So from here, I recopied this here, also noting that d2y dt squared is equal to dy dt, and then taking the derivative a second time with respect to t. And now I'm going to consider the equation I am trying to solve. It is this equation of the form t squared d2y dt squared plus alpha t dy dt plus beta y equals 0. So I've written that equation here. I'm going to start substituting for the d2y dt squared, which we have is equal to the d2y dx squared 1 over t squared minus dy dx 1 over t squared plus alpha t. Now my dy dt, I'm going to replace that with my dy dx 1 over t, and I have plus beta y equals 0. And multiplying through by the t squared, I get d2y dx minus, multiplying by the t squared, dy dx plus alpha t dy dx plus beta y equals 0. Last, I can group my dy dx, and I'll have alpha minus 1. So I have transformed this equation here by using x equals natural log of t, and then just looking at what d2y dt squared and dy dt equal, I was able to transform this equation here into this equation that has constant coefficients. And now that we derived the Euler equations, we should try a problem with it. We will go back to the problem we were looking at the beginning of the video, which is t squared y double prime of t plus 4ty prime of t plus 2y of t is equal to 0. And so this t squared and this 4t, these are not constant coefficients because the t is our variable that y depends on. So we can't just simply write a characteristic equation. We need to use these Euler equations. So we'll look at how we transform this. So first of all, we're going to let x equal natural log of t. And also we're going to note that alpha here, so this follows the form t squared y double prime. Then we have an alpha t y prime, so alpha is equal to 4. And then here we have beta y, so beta is equal to 2. So looking at this, we transform this into this equation here. We have our y double prime, alpha minus 1, that's 4 minus 1 y prime, plus beta y, so that's 2y, or in other words, y double prime plus 3y plus 2ty equals 0. So now we have constant coefficients, right? Our coefficients are 1, 3, and 2. So we can write our characteristic equation, r squared plus 3r plus 2 equals r plus 2 times r plus 1 equals 0, which gives us r is equal to negative 2 and equal to negative 1. So our solution is c1 e to the minus 2x plus c2 e to the minus x. And we have to be careful here because what we used was this x over here. So this is important that you remember your variable here is x. We've substituted x in here. So now we have to get y in terms of t. But we have that x is equal natural log of t. So e to the x, which is what we have here, something of the form like e to the x, is e to the natural log of t, which is equal to t. So now we can rewrite y. So this formula here is something you will definitely be using. It's not just something that came out of this actual particular equation. In general, you'll be using this line right here. So y is going to be c1 e to the x to the negative 2. That will give us our e to the negative 2x, plus c2 e to the x to the negative 1. That gives us our negative x. But that also will allow us to do this part, e to the x will be t. So we have c1 t to the negative 2 and c2 t to the negative 1. And that's it for this video. Thank you for watching.